Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will continue with MAC algorithm, and we will start our lecture from where we finished the last lecture. If you recall, in the last lecture we discussed about advancement of the velocity components in each cell from nth level to a level n plus 1, and these advancements are done in an explicit manner. As we can see here, uijk at nth level plus delta t into condiff u minus dp dx at nth level at a point ijk. So condiff u minus dp dx, this means convective and diffusive terms and the pressure gradient term. So these are minus ddx of u square minus ddy of uv and minus ddz of uw minus dp dx plus 1 by re into del 2 u del x2 del 2 u del y2 del 2 u del z2, and these terms are being added with, after having multiplied with delta t, being added with uijk at n to yield uijk at a level n plus 1, but this is these components, velocity components, have not yet satisfied continuity equation in each cell. So we are calling these velocities as provisionally advanced velocities. So instead of writing uijk at a level n plus 1, we are also using a tilde sign. That means it is not yet uijk at n plus 1, it is provisionally advanced uijk at a level n plus 1. So in the similar way, we can calculate vijk at a level n plus 1, but provisional. So provisionally advanced v velocity, provisionally advanced w velocity, and provisionally advanced v and w velocities, we will have corresponding convective diffusive terms and the pressure gradients. So this way we advance the velocity components or the velocities at each cell from a level n plus 1, from a level n to n plus 1, but these velocities have not yet satisfied continuity equation in each cell, so we are calling them provisionally advanced velocities. So if we really analyze the situation, what we have done, we have basically multiplied contributions of convective and diffusive components of u momentum equation with delta t, and then we have added the pressure gradient term. So minus dp dx, which was pi plus 1 jk minus pi jk by delta x, this is dp dx with minus sign. We are now writing it as pi jk minus pi plus 1 jk by delta x. So minus dp dx we are writing in this way. We are bringing in plus sign here, and so that dp dx is also being multiplied by delta t, so this is multiplied by delta t to produce basically the u velocity at ijk cell at a level n plus 1, but we are using tilde sign because the pressures that we have used in calculating u velocity, those pressures are at a level n. They are not at a level n plus 1. So basically there are two discrepancies. One is these velocity quantities, we are calling them provisional. Why? They have not satisfied continuity equation. Number two, that this has a reason also. These both the observations are complementary to each other. Number two is that while calculating these provisionally advanced velocity quantities, we have used pressure at a level n. We have no other options, we have to use that. But since we are using pressure at a level n, we have to call this something other than n plus 1, which is n plus 1 tilde. Because in the ideal situation, these pressures should be at a level, say at a same level of the velocity. So that is what is the observation with equation 5. And again I am just restating that this is dp dx minus dp dx, and minus dp dx we are writing it in this way. We are bringing in plus sign here. So within dp dx it is pi jk minus pi plus 1 jk by delta x. Originally it was pi plus 1 jk minus pi jk by delta x. Since we are changing the sign, it is now pi jk minus pi plus 1 jk. So this is dp dx into delta t. Now what should have been the ideal situation? Let us discuss that. Ideal situation should have been these pressure quantities, instead of remaining at a level n, these pressures should have been at a level n plus 1. Then we could have written uijk n plus 1. We did not have to use tilde sign, and here we are not using tilde sign. So if the pressures at a level n plus 1, these velocities will evolve as velocities at a level n plus 1, not provisional velocities at n plus 1. These are provisional because these have not satisfied continuity, and another reason is these have used pressure which are at a level n. So conceptually this is the correct equation, although we are using for calculating provisional velocities equation 5. So there is a difference between equation 5 and 6. Now this difference, if we want to really estimate, it is basically then uijk at a level n plus 1 minus uijk provisional, that means n plus 1 tilde, equal to delta t into pijkc minus pi plus 1 jkc by delta x. Simply pijkc means pressure correction. Pressure correction is at each cell is pressure at n plus 1th level minus pressure at nth level. So Pijk at n plus 1 minus Pijk at n is Pijkc. So Pijkc is the pressure correction at IJK cell, and if these pressures are corrected, then instead of Pijk at n, we will have Pijk at a level n plus 1. So we can now establish this relationship, that is provisionally advanced velocity and the velocity which is really velocity at n plus 1th level is delta t into the pressure correction by delta x. Pressure correction at IJK cell minus pressure correction at I plus 1 JK cell divided by delta x. So we can establish this relationship, and we have exactly repeated that Pijk at n plus 1 level minus Pijk at n is Pijk at c, and they are related, pressure correction at Pijk minus pressure correction at Pi plus 1 Jk. They are related to the final velocity which we should have gotten minus the provisionally advanced velocity quantity. So this provisionally advanced velocity quantity and final quantity which we should have obtained, they are related through this relationship with the pressure, and then we can write Uijk at the level n plus 1 will tend to, we have not, because it may not be immediately evolve to that level, because this pressure corrections have to be correct, very very correct, then only we will get Pijkn, and we may require to repeat the calculation. So we are writing Uijk at a level n plus 1. This will evolve if we keep on adding with provisionally advanced velocity quantity plus delta t into Pijk minus Pi plus 1 Jk by delta x. And this Pijk and Pi plus 1 Jk are pressure correction terms. Similarly, then we can write for the velocity quantity at I minus 1 Jk cell. So I minus 1 Jk at the level n plus 1 is again I minus 1 Jk tilde n plus 1. That means provisionally advanced quantity, and this will be corrected in this way. You can easily do this calculation and get this expression. Now we also look at v velocity at the level n plus 1 and provisionally advanced v velocity, and that should be corrected this way through the pressure correction terms. Now Vij minus 1k at the n plus 1 at the level n plus 1. This is basically again provisionally advanced velocity at Vij minus 1k, and this is the correction term. This is the correction term. We are using pressure correction. Effectively, this complete quantity is velocity correction. So these pressure corrections are contributing to correction for the velocity. So similarly, Wij at the level n+1 is provisionally advanced Wij velocity plus velocity correction, which is related to the pressure correction term. And Wij minus 1 at n+1th level. This is provisionally advanced velocity at Wij minus 1 plus the velocity correction, which is Pijkc minus Pijk minus 1c by delta z into delta t. So in each, if we consider a cell which has the proper continuity cell, if you recall that we discussed in the first lecture. So that cell, since this is staggered grid arrangement, on the eastern face we will have this velocity, on the western face we will have this velocity, on the northern face we will have this velocity, and on the southern face we will have this velocity, and one of the sides will have this w component of velocity, and just the opposite face of that side will have a w component of velocity defined by this. And these are the velocities on each face of a cell. And basically, when we write continuity equation for a cell, we involve all these east, west, north, south and two side walls in such a way that we write the difference between them to set up the gradients, to write the del u del x term, del u del y term and del v del c term. So plugging in the above relationship into continuity equation 1, which is del u del x plus del v del y plus del v del z, and neglecting the pressure corrections in the neighboring cells. So you just substitute into del u del x plus del v del y plus del w del z these u components and v components, w components, and delta x, delta y, delta z. You will get on the left hand side this quantity. And at n+1th level, this must satisfy the continuity equation, means this is a continuity equation and this should be equal to 0. But now, instead of becoming 0, the right hand side will be all these terms, will be having all these terms. So basically, again, we can reorganize uijk minus ui minus 1 jk by delta x. Both are provisional velocities. Vijk minus vij minus 1 k by delta y, provisional, and wijk minus wij k minus 1 by delta z, provisional. And definitely this is now non-zero, because if this is 0, if all the terms equal to 0, then continuity has been satisfied. But since we have used provisionally advanced quantity, these bracketed terms will produce non-zero terms, and then there will be pressure terms. And if you look at the pressure terms, these are pressure corrections at ijk cell, I plus 1 jk, I minus 1 jk, then ij plus 1k, ij minus 1k, ijk plus 1, ijk minus 1. So ijk and all its 6 neighbors I plus 1 jk, I minus 1 jk, I j plus 1 k, I j minus 1 k, I jk plus 1, I jk minus 1. Those all pressure corrections terms will come here. Now you see we have written a special attribute that neglecting pressure corrections in the neighboring cells. So we just retain pressure when we sum up this pressure corrections at ijk cell. So pressure correction at I plus 1 jk, I minus 1 jk, I j plus 1 k, I j minus 1 k, I jk plus 1, I jk minus 1, we are neglecting. And definitely this is, this may not be proper to neglect that. And for that we have to really pay some price. We'll see that also. So by neglecting, we can write this term, which is equation 13. And from equation 13, then deliberately we neglected. You can also sense why we neglected, to get rid of implicitness, so that we get an explicit expression for pressure correction. So from equation 13, we get pressure correction at ijk. I'm going back again. At ijk, you can see. So this will be, then if this is 0, ideally this is 0, so then and this is non-zero. So this provisionally advanced velocity, what they will produce in each cell, we will get that as non-zero divergence. So non-zero divergence divided by the coefficients of Pijk term. So basically then Pijk correction is divergence at each cell. This divergence is basically arising out of the provisionally advanced velocity components divided by twice delta t, 1 by delta x square, 1 by delta y square, 1 by delta z square. These were basically the coefficients of Pijk term. We are clubbing them together and transferring on the right hand side. And we are supposed to get pressure correction through this, but we are advancing accelerating our pressure correction. We are using over relaxation term. The value omega naught, this is over relaxation factor, giving most rapid convergence, should be determined through numerical experiments. Numerically, one can, there are ways to experiment with it. Usually the value which we use, I can give you the value. It lies between 1.5 and 1.7, but one can do also testing, a priori testing, to choose a correct over relaxation factor, or I should not say correct, more appropriate over relaxation factor. So after calculating Pijkc at each cell, we can correct the pressure. So pressure at nth level, we add pressure correction, and we are supposed to get Pijk at the level n plus 1. But see, you can jolly well understand that we neglected all the neighboring terms to get this explicit expression. So you cannot expect that this pressure correction is really the exactly correct final pressure correction term. And that is why here also we have used, instead of equality sign, tends to sign. So pressure has to be corrected, and after having the pressure correction, we add it with nth level pressure, we get improved Pijk, but that is not final Pijk. And we repeat this calculation. what we did, and maybe some finite time of setting some loop and maybe calculating it iteratively. It may take 100 iterations, it may take 200 iterations, or whatever the number of iterations. But finally, when the correct velocity quantities will evolve, divergence will be zero, there will be no further pressure correction, we'll get the correct pressure, and by that time all the velocity terms have also evolved as correct velocities from provisional to corrected final velocity. So this is basically called pressure velocity iteration. Now this pressure velocity iteration procedure, if we really look at it, it is basically the way we are solving pressure correction. We can call this as a solution of Poisson's equation for pressure. And this can be shown also. Just I will show you in the next slide. If we do not ignore the pressure corrections in the neighboring cells, then the pressure correction equation may be written as Pi plus 1 jk C minus twice Pi jkc plus Pi minus 1 jkc divided by delta x square. Similarly, instead of Pi jk delta y square, we will retain Pi j plus 1k Pi jk minus twice Pi jk plus Pi j minus 1k. So these two neighbors are retained by delta y square, and in basically the term associated with Pi jk by delta z square are Pi j k plus 1 and Pi j k minus 1. So these neighbors like Pi plus 1 jk, Pi minus 1 jk, Pi j plus 1k, Pi j minus 1k, Pi jk plus 1 and Pi jk minus 1, all these correction terms, if those are written together with Pi jk correction term, Pi jkc, then we will get left hand side of the equation like this, and right hand side will remain the same. Basically this is the continuity equation written in terms of provisionally advanced velocity components. And then you can see that we cannot directly get an explicit expression for pressure correction at ijk point. Earlier we got an explicit expression for P ijk correction or pressure correction at ijk, but here we cannot get that. All the neighbors are present, pressure correction terms. So what we have to do, we have to vary I from 2 to IRE. IRE means the maximum number of cells or maximum number of points, something like I max minus 1. So here of course the domain is I is 1 to IIM. So this is IIM minus 1. So because the extreme points like IIM on one extreme and one at the other extreme, these are to be taken care of by the boundary conditions. So varying I from 2 to IRE, J from 2 to JRE, and K from 2 to KRE and applying boundary conditions, we can obtain a system of equations that can be written in the form AX equal to B. That is, A is the matrix, X is the unknown vector, and equal to B, B is the right hand side known vector. A is a septadiagonal matrix, and the system of equation can be solved by setting up a linear solver, linear equation solver. Today, quite a few advanced open source linear solvers are available, like by CGStab or Hypre, etc. Those can be linked also, but at the moment, we will not go or will not take up our discussion to that direction. What we can say that basically, one can solve the pressure correction equation also this way by setting up a matrix and having the pressure correction terms solved directly from the matrix. But as you know, setting up such matrix equation and solution techniques both are very much involved. That is why the first option that we discussed, that explicit form of pressure correction equation, although we are ignoring neighboring points, that is why you need to iterate the process or the pressure correction and corresponding velocity correction. Number of times, iterations can go to 200, 300 times and continue for 200, 300 sort of iterations, but solution technique is straightforward and simple. Here also you can see if one desires to go for this way, that this can also be done, but developing such a solver is quite involved and requires special effort. I have also mentioned that the domain extends from I equal to 1 to IIM, j equal to 1 to JIM, and k equal to 1 to KIM. These are the maximum number of points in respective directions. Now we will discuss about the boundary conditions. Boundary conditions are imposed by setting appropriate velocities in the fictitious cells surrounding the physical domain as seen in the figure. So what we can see in the figure, that basically on each side we have fictitious cells, and these fictitious cells, they participate in computation because we get our boundary defined by setting up the velocity values in the fictitious cells in such a way that all the desirable conditions for impervious boundary or no slip boundary or free slip boundary, those are properly described with the help of fictitious cells. But when we do the post processing, obviously we need not pay attention to the velocity values in the fictitious cells because that is outside the physical domain. So fictitious cells are also called imaginary cells, and as you can see that they are outside the physical domain. Like in x direction, for example, the physical domain extends for I equal to 2 to I equal to IRE. But IIM and I equal to 1, these cells are all imaginary cells. Similarly, in J direction, J equal to 2 to JRE, this extent, these cells cover the physical domain. But we have nomenclature wise J equal to 1 to JIM. So all these cells at JIM level, all these cells at J equal to 1 level, these are fictitious cells. And these are used for, as I have said, that setting up correct boundary conditions for the velocities at the planes where velocities are not directly defined. So what we can conclude from this slide, that in x direction we have I equal to 1 to IIM cells. In y direction we have j equal to 1 to JIM cells. In z direction we have k equal to 1 to KIM number of cells, and cell width in x direction delta x, in y direction delta y, in z direction delta z, and the real physical domain when we try to identify the physical domain will exclude imaginary cells. But imaginary cells are very important because they participate in computation to set up the correct boundary conditions at the confining walls. Because many a times for staggered grid, you will not get velocity components are directly defined on the planes of interest. And immediate example is stationary bottom wall. So if I'll go back by one slide, bottom wall, that means if you exclude imaginary cell and the domain where physical domain described by this all these internal cells, and the domain boundary, that means stationary bottom wall, for example. This is if we exclude one layer of imaginary cells, just the top of that layer, the bottom boundary exists. And that but since bottom boundary exists on the top of one layer of imaginary cell, bottommost imaginary cell layer, so we have to see how we can set up the boundary conditions so that the rigid no slip bottom wall can be defined. We have defined Vi1k, this is a normal component of velocity, and I equal to 2 to IRE, k equal to 2 to KRE, we will vary, and all V velocities, if you imagine the bottommost layer of cells, all V velocities are falling directly on the bottom plane, so we can set them equal to 0. But UI1k, these cells are defined at the middle of the bottommost cells, not falling on the boundary. So the velocities at these cells UI1k are to be interpolated with UI2k in such a way that the bottom wall can be defined, or on the bottom wall U velocity satisfies the no slip boundary condition. u equal to 0. This is impervious boundary condition. Normal velocity equal to 0, and u and normal velocity equal to 0, v I1k equal to 0, and u and w, these are tangential components of velocity. So these are to be interpolated with the immediate upper layer of cells in such a way that bottom boundary is created as no slip boundary. So ui1k equal to minus ui2k, wi1k equal to minus wi2k, I equal to 2 to IRE, k equal to 2 to KRE. Now this is how we set the boundary condition, velocity boundary condition in such a way that immediate at the top of this layer of imaginary cells we define a rigid no slip wall. Similarly, for example, if we want to define this plane, which is on the left hand side, if we exclude imaginary cell, the plane which we will get on this domain, if we want to define that plane as free slip wall, then what we have to do? We have to set up the boundary conditions in the following way, that the normal velocity must be 0 on that plane, and tangential velocity should have no normal gradient. So that means normal to this plane is basically w component of velocity. We can directly set those velocities to 0, and but we have to interpolate u and v component in such a way that physically this plane becomes a free slip plane, which is describable by del u del z and del v del z equal to 0. So del u del z, del v del z equal to 0. That means u ij1 equal to u ij2, j equal to I equal to 2 to IRE, j equal to 2 to JRE. We'll describe the plane. Similarly, Vij1 equal to Vij2, del v del z equal to 0. Del u del z equal to 0 is deciding u boundary, u velocity boundary conditions, and del v del z equal to 0 will dictate basically boundary condition on v velocity. On the plane, I equal to 2 to IRE, j equal to 2 to JRE, and k equal to 1. K equal to 1. These boundary conditions are, first set of boundary conditions were for rigid no slip wall. Second set of boundary conditions are for free slip wall or vanishing shear boundary condition. Now on the front plane, for example, this is there is no fixed prescription for that. Front plane, you can or we can set up, we can define the velocities the way we like. It can be experimentally obtained velocity profile. It may be uniform velocity profile. It may be parabolic velocity profile. So and we have to set up a function on, basically this is jk plane, and in the I direction we have to set up a function to describe the proper profile. Like if we want to set up a parabolic velocity profile, what we have done, v velocity we have set to 0. Basically, you can see v1 jk equal to minus v2 jk. Here j equal to 2 to jre and k equal to 2 to kre on any I plane. Basically will vary j 1 to j extreme, j2 to k 1 to k extreme. That will describe any plane in I direction. So at the entry I equal to 1, but j will vary from 1 to j max or j im. K will vary from 1 to k im, but one need not be included in setting up the algorithm, because if we set k equal to 2, the boundary condition will be inducted with that. So v1 jk equal to minus v2 jk, w1 jk equal to minus w2 jk, and so w component and v component velocity we are setting on that plane as 0, and u1 jk equal to 1. This is basically uniform velocity profile, and u1 jk equal to 3 by 2 into 1 minus y by ym square. This is basically ym is the horizontal midplane. This is jm minus j divided by jm square. So basically setting up, we are trying to set up a parabolic velocity profile. So v1 jk equal to minus v2 jk makes v on this plane, inflow plane 0, w1 jk equal to minus w2 jk also make w velocity 0, and u either 1 or parabolic or any other profile we can set up by describing a mathematical function representing the profile, and j equal to 2 to jre and k equal to 2 to kre, that is basically any cross plane will be covered by this loops or these variations. J equal to bottom to top extent, k equal to one side to another side, will give the cross plane. So that is how we have we can set inflow plane, inflow boundary condition on the inflow plane. Inflow plane exists here. One can understand by looking at the geometry. Now we will go for continuity or outflow boundary. Now continuity or outflow boundary, if we have to set up outflow boundary, so basically we have to give boundary conditions here, right? If we exclude one layer of imaginary cells at the extreme side of the geometry, the extreme downstream of the geometry, so basically we have to define exit boundary here. Now there is a catch with the exit boundary, because exit boundary condition is not known. If had we known, had we known the exit plane velocities, we would not have solved this governing equations. These are not known, but since we are solving a problem which is elliptic in space and parabolic in time, we have to prescribe boundary conditions for all confining surfaces. Out of this compulsion, we have to set up some functions at the outflow plane which depicts correct flow physics. Now, one can very easily imagine a set of conditions like first derivatives of velocities as 0 in the flow direction. So basically x direction is the flow direction. So del u del x equal to 0, del v del x equal to 0, del w del x equal to 0. That is a plausible boundary condition. But these boundary conditions are first order accurate, but not wrong either. Only thing, accuracy can be enhanced. If you look at physically, del u del x equal to 0, del v del x equal to 0, del w del x equal to 0, these boundary conditions also in a way conveying the message that acceleration is 0. Spatial acceleration is 0, which is one form of restriction. Actually, it will be better if we do not impose any such restriction. Outflow boundary should be a free boundary. Physically, the flow should have a smooth transition, or smooth transition from the flow domain, smooth exit from the flow domain. So the boundary condition that has more generality at the outflow plane is described by Orlansky. This was a very well-known, referenced also paper in Journal of, this was published in Journal of Computational Physics, and these conditions are called Orlansky condition, which is basically del psi del t plus u average into del psi del x, where psi stands for the dependent variables u, v, w, t, all the if you have energy equation, it is also imposed on T, temperature. So U, V, W, T, psi represents all those variables, and del psi del T plus U average into del psi del X equal to 0. And this U average is the basically average velocity at the exit plane. And obviously, when we are computing for a given time step, it is not known at that time step, so it should be known from the previous time step. So from the previous time step value or values, U average has to be calculated, and that U average has to be prescribed here. And then we'll be able to set up a very correct boundary condition on U, V, W, and if you have temperature also, energy equation, when you are computing on T also. Now, you can see if you use simply, first derivative equal to 0, or if you use Orlansky condition, whatever we do, we are basically setting up boundary conditions that are Neumann type. So, if the velocity boundary conditions are Neumann type, the pressure boundary condition has to be Dirichlet type. And indeed, we do that. What we do, we set up the pressure boundary condition or pressure at the exit cells as the base pressure. base pressure of the domain. As we know that every iteration pressure is being corrected, so through pressure correction, all the upstream cell pressures are corrected in order to set up a correct pressure gradient in the domain, but exit plane pressure remains as the base pressure. We do not correct exit plane pressure. Having said this, so we have covered basic flow solution strategy, boundary conditions, all related pressure velocity iteration. Now we can see that since our governing equation is elliptic in space, parabolic in time, so we will basically march in time direction. So the time step will have stability requirement. And if you recall, for such equations where it is elliptic in space and parabolic in time, we pose both the restrictions on the time step. One is basically restriction which is known as Courant-Friedrich-Levy condition, or the restriction on Courant number. Now that means at each cell Courant number should be less than 1, and local Courant number at each cell is defined by, for example, in x direction u delta t by delta x, in y direction v delta t by delta y, and in z direction w delta t by delta z. So delta t minimum over the domain we can write this way: delta x by modulus of u, u may be locally negative or positive, delta y by modulus of v, delta z by modulus of w, where the maximum is with respect to every cell in the mesh, and minimum is also with respect to every cell in the mesh. So basically this for in each cell, whatever is the Courant number corresponding the cell velocity at that cell, from there we can calculate delta t, and here minimum over the entire domain we calculate delta t. Typically delta t is chosen equal to, finally see this minimum, less than minimum of this delta t at all cells based on Courant number in x direction, y direction and z direction. That is well, but and it is less than minimum of that, but how much less, that also one has to know or estimate. So typically delta t is chosen equal to 1/4 or 1/3 of the minimum cell transit time. So delta t in each cell is calculated, from that minimum is found out, and whatever is that value, usually 1/3 or 1/4 of that value is used for time advancement. That is from one side, and then we can apply Neumann stability condition also. And von Neumann stability restriction means it is on grid Fourier number. That means it is on the coefficient, in this case nu delta t by delta x square, or nu delta t by delta y square, nu delta t by delta z square, and nu delta t will be minimum of all these, and this can be summarized as equation 19. From here, we can, if we non-dimensionalize, then we will get delta t less than half into delta x squared, delta y squared, delta z squared divided by delta x squared plus delta y squared plus delta z squared into Reynolds number. So delta t is less than this quantity given by equation 21. The last quantity, so now equation 21 gives indication of delta t. Also equation 18 gives indication of delta t. We calculate basically both the delta t's in the program and use minimum of these two. Effectively, finally use minimum of these two. So whatever delta t we get with for Neumann stability analysis, and whatever delta t we get using Courant number or Courant-Friedrich-Levy CFL condition, we get delta t which is minimum of these two delta t's. The last quantity needed to ensure numerical stability is the appoint parameter alpha. You recall that in the discretization we defined this alpha, which is contribution of basically appointing, and this appoint parameter is alpha. In general, alpha should be slightly larger than the maximum value of u delta t by delta x, v delta t by delta y occurring in the mesh. That is, maximum of u delta t by delta x, v delta t by delta y, w delta t by delta z over the whole domain. Whatever value we get, alpha is slightly larger than that but less than 1. As a ready prescription, a value between 0.2 and 0.4 can be used for alpha. If alpha is too large, an unnecessary amount of numerical diffusion or artificial viscosity will be introduced. So alpha is needed for stable calculation, that we know, but this alpha value should be minimum so that the formulation tends towards second order accuracy. So for that, alpha 0.2 or 0.3, or even we can use 0.1 if there is no problem related to stability. So that should be experimented. Numerical experiment can be done that how small alpha we can take so that formal accuracy or overall accuracy of the discretized equations remain high, remain second order spatially. Now, as you can see, I have given a basic flow chart. Start, read input parameters, compute problem constants, set initial conditions for the problem, compute initial guess velocities. Now at 2000 level, these levels have been given numbers. That means these levels are basically signifying different sections of the code, different sections of the program. Set boundary conditions. If you have additional boundary condition, that means we have only discussed confining boundary conditions. This may be a flow where you have many obstacles inside. Maybe, flow past circular cylinder, flow past a sphere, flow past a square cylinder, flow past any other object within the computational domain. So set up those special boundary conditions to describe the obstacle. Then have the pressures converged. If it is converged, fine, go out. If it is not converged, then update cell pressures and velocity. This is so-called pressure velocity iteration, which we have already discussed, at the 3000 level. So this loop is set. It will keep on iterating, and it will ask whether pressure has converged. If pressure has converged, it will go out of the iteration loop. If it has not converged, it will again enter the loop. If the pressure has converged, that means at a level, if we have got correct pressure at each cell, correct velocities at each cell, that means divergence free velocity field, we have gotten the solution of velocity and pressure for that time level. So we can then print and plot. But if that is not the right physical situation, that means if it is unsteady flow, then of course it will keep on continuing. But if it is a steady flow and we need some more iterations to reach the steady state condition, then we will outer loop again we will activate. So advance the time cycle. So one is outer loop to advance in the time cycle from n to n plus 1 to n plus 2 to n plus 3, and another is inner loop for a given time step or a given level. We have to get converged velocity and pressure field. So this is the overall flow chart, and then depending on the requirement of the problem, this can be modified, like this time to stop this loop, either for you go for steady state computation, or maybe you go for some desired level of unsteady flow, and all those things can be done. And all intermediate unsteady flows, if we want to store, we will have to make use of this level, 5000 level. Here it is written print and plot. So that means we can print the values, we can plot the values, or we need not even do either of these. We can simply create a data file. We can store the data in a file and come out. So that is the loop for computation, and this is a basic flow chart. Thank you. We'll stop here today. In the next class, we will extend our analysis little further. We will take up energy equation, and we'll try to give examples of possible flow fields and its associated energy equation and temperature field. Thank you very much.